to answer to this question in the next slides with some practical examples of how can we do. For instance, for the virtualization and the cloud, this is a good question because the links are connecting the BBU and the radio head are based on fiber, not on satellite. Can we put a BBU inside the satellite? Maybe to be convenient because the resource can be shared by a lot of persons over very wide areas, but there are problems that should be solved. Let's start with the SDR tool, what the SDR can do in the framework of Space 2.0 vision. Typically, the SDR make the satellite payloads reprogrammable and reusable. The reusability is one of the key features of modern networking. Because the non-reusability is one of the most convincing argumentation against satellite. And indeed, when a satellite is launched, its payload is frozen during all the satellite lifetime, that is in general more than 20 years. How many things may happen on the Earth in 20 years? Let's have a look to the decade, to some double decades, starting from 1969. In the summer of 1969, there was the Woodstock concert. Do you recognize Jimi Hendrix with his guitar? And some months before, in October, the first core of the internet was established by Professor Kleinrock at the UCLA. The first two letters were sent to the network. Typically, the first message should the login request. L, first letter. Okay. And by telephone, L was received. Okay. O, okay. And O received. G, nothing. Close the telephone. So actually, the experiment should have been considered a failure, but at least two letters were sent and received in the 1960s. 20 years after, 1989. Please take into account that the satellites launched in 1969 were still active in 1989. Some of them is still active nowadays. In 1989, the Berlin Wall collapsed, and the GSM standard brought the cellular connectivity everywhere. Let's, 20 years after again, 2009, Barack Obama, the first black president of US, and the LTE brought the broadband connectivity everywhere. The smartphones were invented, and in the deep sky, the satellite sadly remains the same. The world changed, but the satellite did not change. And so this is one of the argumentation that made some person to say that satellite is useless for this reason. But in order to counteract this very convincing argumentation, the researchers started since more than 30 years ago to think to programmable payloads. And the first example has been presented during a conference of the ESA, of the European Space Agency. The work is dated 1988 and presents a first programmable payload based on a Texas Instrument digital signal processing processor. Performance quite trivial as compared to the performance of current FPGAs of dedicated processor, but at those times it was the top of the state of the art. The data rate supported is 32 kilobits per second. The receiver, the software receiver, performs both equalization and Viterbi decoding. The Viterbi decoding was moved inside in software in this processor instead using the usual chipsets. The programmability was limited to these two transmission modes. The uncoded 4 PSK and the trellis coded modulation with 8 PSK. So this is what the degree of programmability of this device, of this payload, to select the modulation. Very poor, I agree, but it was the first work breaking the wall of the fixed payload without any chance of updating. Software-defined radios for satellite produces other more interesting examples. For instance, in the recent time, the ESA produced, for instance, a full reprogrammable satellite modem to support the different telemetry and control protocols of the different satellites. So this is a very advanced device as compared to the previous one. This kind of technology is not commercial, and it's very expensive. The flexibility and the programmability of the payload, in this case, for the critical functions of telemetry, tracking, and control that are needed to leave the satellite in its orbit, this technology is out of the shelf. But surprisingly, the current trend is different. The most recent trend in software-defined radio for satellite communication is investing in the CubeSats, the SDR-based CubeSats. One might think, but why? The CubeSat is small, light. In general, it supports low rates. But the CubeSats have a very significant, a very strong point in favor. The cost of the CubeSat is very low, both in terms of implementation and in terms of launch. So, if I want to experiment something of really advanced and risky on a satellite, it's more convenient to experiment it on a payload, on a CubeSat, rather than on an expensive low Earth orbit satellite, or or a very expensive geostationary satellite. Low cost means acceptable risk of failure. But some works like that mentioned in the footer demonstrated that the software-defined radio implementation in the CubeSat is feasible and advantageous. How is feasible? For instance, the ground station can be implemented by using the USRP boards that are not very expensive and they are easy to be programmed. A computer and a couple of USRP board, one for the uplink transmission, the other one for the downlink, can easily implement the ground station. And on board of the CubeSat, we need a dedicated processor based on FPGA that should implement the baseband processing related to demodulation, decoding, and symbol symbol retrieval. Nothing impossible. Indeed, the authors of this paper, affiliated to a Turkish university, the Bogazici, built and launched their payload. The CubeSat 10 centimeters per 10 centimeters per 10 centimeters, with inside the SDR processor and all the components needed to the payload to survive, like for instance the conditioning system for the temperature, the battery, and so on. The vision of the payload. This is a processor. The FPGA processor is on top, and here there's the battery. So they launched this device, this satellite, and the authors of the paper received the data on the Earth with the expected performance. So it's not impossible. So the programmability, they can change modulation, demodulation, channel coding, data rates, everything. The link is flexible and reprogrammable. But there are even other cheaper implementations. Very, very cheap. For instance, in a very recent paper, this one, there was the idea of integrating in the ground station using the programs, the GN radio with the hack RF board, and on the payload to use the integration of a Raspberry Pi, that is very, very cheap component, and the HackRF1 again. So, considering that on sale there are complete CubeSat kits with RF equipment available at 750 USD, this kind of hardware could have a cost of, I think, 300 euros, and so this guy, emerging from Walt Disney Comics, could say, I created my personal satellite in my home lab. Why don't you try?
It's in Earth, not in space. It's 750 is in Earth.
Yes, but they tried it in the lab, and then it should be launched. But by the way, the technology used in this configuration is really technology for home labs.
But what is the cost of antennas on the ground, for example?
If you don't pretend to have high data rates, probably the cost is affordable. But by the way, this is a kind of joke. You know, this guy was really the ancestor of was really substantially. Guys like Steve Jobs and Bill Gates reflects this philosophy, the philosophy of this inventor, of this Walt Disney inventor. But because this philosophy is typically American. The US, in US there is the philosophy that if you have an idea, work to realize it. It will be feasible if you want. Apart this joke, the increasing trend of the CubeSats is really impressive. So the number of CubeSats launched in the sky is exponentially increasing with the time, because the CubeSats allows to launch a payload that is tailored on your expectations and applications. And the experimentation of software-defined radio through satellite links should not neglect this possibility, because you can realize a kind of a homemade satellite, or at least a satellite constellation designed on your expectation, and considering the reconfigurability features that the software-defined radio can offer. It's much more difficult to experiment advanced technologies over bigger satellites. So the bigger satellites, big satellites are implemented by big companies that have to face the risk of the failure. Risk of failure means risk of losing millions or even billions of euros in big missions. The small satellites allows to risk and